Kill the guy now. You have the gun. Hit him. What's wrong with you?
What?
Good day, sir.
You are watching Jackie Pan in my house.
No, it's King Kong, sir.
King Kong. You've never heard of ACTV before in your life? ACTV is very educative, informative, and there are football sport there. There is entertainment. There are a lot of things you can even attend lectures here. All you know is watch all those nonsense artists and do nonsense, or you watch nonsense on TV. Last night you almost came in bed with your fist.
It's not me, sir.
You wake up every morning, the bed will be so rough, like you've been fighting for in your dream. That's the reason why you have F's in your courses, like especially made for you.
I have V last semester.
We by pounds on you. Very stupid though. Change that section to ACTV right now. And oh God, the baby wants to have the first born. Stupid boy.
Good day, everyone, and welcome to MT201 online lecture. We have started the lecture we have taken 12 classes on this online platform. And today we're going to continue our lecture. Last time, we started the convergence of series. We discussed some examples and some theorem, but this afternoon we are going to continue from where we stopped. If you can remember last week, the last example we discussed was example 2.13 that says the harmonic series of partial sum n from 1 to infinity, 1 over n is a divergent series. Today we want to state a theorem. We'll prove the theorem, then we'll go to another section of this convergence of series. And the theorem is this. Theorem 2.2. Theorem says, suppose that the sums n is equal to 1 to infinity of un and n is equal to 1 to infinity of Vn converge respectively to U0 and V0, then, yes, 1. Okay, let me call it 1. The partial sum of n is equal to 1 to infinity of un plus Vn will converges to u0 plus V0. Then 2. The partial sum of n is equal to 1 to infinity of constant un converges to constant u0, where my C is constant. C is a constant. I'll prove this A. I'll leave this 2 for you. But see the proof of the one. It's very simple. What you need to do is one part of the first one, just U part of the first proof, to mimic it. Then you put constant, just like that. The constant can be multiplied, the constant can be added, it can go inside this sum, it can come out, whatever you like it. But just one part of this proof is sufficient for this second one. Now, you remember, if I have un, u1, u0, u1, u2 to un and u infinity, which is the sequence of the partial sum of the series, and I want to say the sequences or the series converges, then I will say limit n tend to infinity of my un is equal to u0. If I write this one, I've not started proof. Don't forget, if I write this statement, what I'm saying is that this series converges to U naught. Now, what I would do to prove this, brother, is that I would define this UN as a variable, as a quantity. I would divide this Vn as another quantity, that this is sum of the series. Then when I divide, I will write them in this form. When I write them in this form separately, I will combine them. If I combine them in addition like this, then I want to see what will come out of it. If I can get this value there, then I will say my statement is correct. Now let us go. The proof. Look at, let sk equal to 1 to infinity of un. Don't forget I can call my un to be s. Yes, sum of this series. But because there are two of them, I want to name the first one sk. I want to name the first one sk, and I will name the second one sk prime to be equal to n is equal to 1 to infinity of vn. If I name that one, then if I have two of them, let me add two of them. Don't forget this is a sum. It's not a number. I just represented them by sk and sk1. Then if I have two of them, the sum must be different. If this is 2, this is 3. If I add 2 and 3, I will not have the same answer. The answer will be 5 if I have 2 and 3. But now I don't know either this one will be 5. Let me add two of them. If I want to add two of them, I have to represent them by another variable. Let me represent by sk prime prime. Then it will be equal to the sum to n is equal to 1 to infinity of un plus vn. So if I have that one, if I have this, I can separate this sum for this. This can go for this can go for this. Then it means sk prime prime can be equal to sum of un of n is equal to 1 to infinity plus n is equal to 1 to infinity of vn. Now I've written them separately. My problem is this. Can you see? I have, from the sum, I've gotten this brother and this brother. The problem is to change all those n to naught. The n to 0. Now, but let me now make a statement to where I have started, what I reminded you. I will not write all these brother in form of limit of the function. Instead of this sum, I would change them to limit of function. But don't forget, this place was named sk prime. So now, since n is equal to 1 to infinity converges, yes, to, if I want to write converges next time, I will not write converges. What? Let me write it, because if I continue to write this logo, some people will read it as tend to. But let me just, if this one converges to x0, then the limits n tend to infinity of sk, this brother is sk, isn't it? Of sk is equal to u0. Also, if this brother n to infinity of vn converges to v0, don't forget I was not the one that said that. It has been stated in the theorem. To v0, then the limits sk prime will be equal to v0. Now, having stated that, look at their sum. Their sum here says the limit of this sum of n tend to infinity of
sk prime prime, the limit can be equal to limit of n tend to infinity of sk plus sk prime. Yes. If that is the case, this one can be written as a limit of n tend to infinity of sk plus limit n tend to infinity of sk prime. But don't forget, what is the limit of this idiot? What is the limit of this brother? Then this one is equal to u naught plus v naught. That is the end of the... Okay, no. Because of the statement of my proof say, if that one, then this statement, then I'll prove the converse of that theorem. But from this first statement, I've this one, I want to get proof from this brother and get this now. From this one is out. Then from here, I'll go back. It's just like I want to start what I've done here, but I'll just summarize it, and then everything will come out. Conversely, u naught plus v naught is equal to limit n tend to infinity of sk plus limit n tend to infinity of sk prime. Can you see this one to this one? Can you see it's like I'm going up, and this one will just give me this brother. From where I've written this brother, where is it? Don't forget, this brother was derived from this one. This brother was derived from this one. Can you see this one, this one, this? Though I can now write this one in form of n is equal to 1 to infinity of un plus o. This partial sum of n is equal to 1 to infinity of vn. So if I've written that one, then I can combine. I want to jump some steps. I can combine the two. This one will come out. These two will be in that bracket. I can write a sum for them. This sum outside. Then the other, this un plus will go inside. Like this, but this step. Like this step. But from this step, I can easily jump and write this one. Okay, let me just write. This one is n is equal to 1 of un plus vn. This brother now is this uncle. Can you see? I've proved from here to here and from here to here. And that is the end of the proof. So it means if I have two convergence series, if I take the sum of the series, then the series converges. If I want to state it in exam, I may not state it like this. I used to tell you, I will tell you, prove that the sum of two convergence series converges as their sum. This is the sum of their convergence. I told you this is the limit of u, this is the limit of vn, and it converges at that point. Okay. Let me quickly go to test for convergence because of my time. Test for convergence. Yes, I want to skip the 2.3 theorem because 2.3 theorem is just the first part of only one there. And you see it is just straightforward. Use the Cauchy sequence, prove that one, you see there. But let me go to test for convergence of series. Yes. Test for convergence of series in this aspect. No, there's many people. They sat down, they will say, oh, let me look at this series, harmonic series, alternating series, and so on and so forth. And they develop a method to test either the series has a limit. And at that limit, does that limit exist? If it exists, then the limit converges. Sorry, the series converges to that limit. Then we want to see how they go about to test for convergence of different series. You know, for example, there are 4 of them. Yes, let's say there are 4 of them. We have the Lambert ratio test. We have integral test. We have nth root test. We have the last one is P test. Now, if, for example, if you want to go for a harmonic series we consider that day, 1 over n, you cannot use the Lambert theorem to test, ratio test, to test for convergence of harmonic series. You cannot. You can only use integral or nth root to do that. Or, sorry, Leibniz theorem to do that. But we want to go, I said there are 4 of them. There are 4 of them. Or let me say there are 4 of the tests. Number 1 is integral. Integral test. Number 2 is this man is from Nigeria. The Alabat ratio test. So this is the Alabat ratio test. Number 3, nth root test. And number 4 is Leibniz test. Leibniz. So Leibniz test. We are going to discuss one by one, but not today. We are going to start from nth integral. I'll just rush through integral, and then I'll go to the numbers. We'll call it a day, if the time will permit us. Yes, what does integral test state? How does it define its own process? Now, let me remind us something. We discovered that we said a series is monotonically increasing if an plus 1 is greater than an. Yes. This is, no, greater than equal to is monotonically increasing. But if I didn't put this one, it is strictly increasing. The monotonic is strictly increasing. But if I put this one, then I will say it's increasing. Because if I say something is equal to it, may at a point they have the same value. But if it's strictly increasing, it is ordered said 2 can never be equal to 1. 3 can never be equal to 2. So that is what this man says there. That if you have a monotone decreasing sequence, that is an plus 1 none less than an, monotone decreasing. If the decreasing function is given in that way, this function is function of n. I can represent it by f of n. I'm not writing notes, I'm explaining that note for you now. Can be represented by f of n. So if I want to use integral test, I can change this function to f of x. I will change it to f of x. At the point I change my function of n to f of x, I will not take the sum of my n from 1 to infinity or from 1 to n for convenience, from 1 to n. To make it convenient, if I take the sum of my series to 1 to n, then I will tell you can use it to test for convergence. Because if I leave it at f of n, I'm still taking the limit of my n from 1 to n, then the loop, stupid, it does not have any meaning. But if I change my function to variable of x, then it gives me what I need. And that is what that man says about its own theorem. Okay, let us consider an example. Integral test. Theorem says it. Let me do the example 2.14. The function f of n is equal to 1 over n raised to power p is a sorry, let me change that question this way, because it's like the solution has been given to you. Show by integral test that the series, yes, n is equal to 1 to infinity 1 over n raised to power p converges for p greater than 1 and diverges for p less than or equal to 1. Yes, there are two cases. This one will converges if p, this one will converges if p is greater than 1. This one will diverges if p is less than or equal to 1. But what will happen to this brother if p is equal to 1? Let us see the cases. Then we are done. Very simple. Solution. If you see this series, it's a monotone decreasing series. It will continue to decrease. Okay, argue it out. Look at this. If my, let us take the value of p to be any value now. Let assuming 2 greater than 1. Let assuming p is 2. Because if we take p to be 1, then everything will blow out. If p is 2, don't forget at n is equal to 1, this one will be 1 over 1 raised to power 2. That's 1 over 1. The next one will be 1 over 2 raised to power 2. That is 1 over 4. The next one will be 1 over 9. Those who know that 1 over 9 is less than 1 over 4. So it's decreasing. So in that case, I said the function is a decreasing function for all n in natural number. And let f of x be equal to 1 over x raised to power p. Instead of my f of n. No, this f of n will be equal to 1 over n raised to power p. And I say it's a decreasing sequence function. So if this is what I change my this brother to f of x, integral test, we are going to integrate this. We are going to integrate this. Then the integral from 1 to n. Let me change my sum to from 1 to n of 1 over x raised to the power p dx. We want to integrate this brother. This one will give me as 1 to n over x raised to the power p, no, minus p dx. Yes, that's what that one give me. And this one will be simply, don't forget the integral will add 1, will be 1 minus p, x will raise to that, and over 1 minus p, as opposed to write minus p plus 1, is the same thing. Then at the limit 1 to n. At the limit 1 to n. And this brother can be written as 1 over 1 minus p into x raised to the power 1 minus p into this, into that. That one, they are the same thing. Now, from this brother, I can test anything. If I want to expand it, the limit 1 over 1 minus p, half of us put this one to give me n raised to the power 1 minus p minus 1. N raised to the power 1 minus p minus 1. Upper limit minus lower limit. Because if I put 1 raised to the power 1 minus p, everything will be 1. Whatever p is. Because now, if or let me say for P equal to 1. If my P is equal to 1, what will happen to this integral? What will happen to this integral? Then I will have integral of 1 to n, 1 over, sorry, f of x dx is equal to 1 to n, 1 over x dx. Yes, if p is 1, that's what I will have. Then this one will give me log x into 1 to n. If I integrate that one, then at this moment, this one, integral of log 1 is 0. Then I have log n. Log n. And that is what I want to be. And if I take the limit of this logarithm as this n tends to 0, the tends to infinity, then the limit of this function will be infinity. That is why I will not say limit n tends to infinity of this integral f of x dx is equal to limit n tends to infinity of log n, and that is equal to infinity. Let me rush and do the second. That is for n if p is equal to 1. But what of if my p is not 1? If my p is not 1, look at this. For p less than or equal to 1, if my p is less than or equal to 1, I will have limit n tends to infinity, integral of 1 to n f of x dx. We are still using this brother. F tends to infinity of 1 over 1 minus p n is power 1 minus p minus 1. Yes. If I have that one, if my n tends to infinity, all this brother will be equal to 1. All these will be equal to 1. And this one will be equal to 1 over 1 minus p. If my n tends to infinity, all this one will be 1. It will be 1. All this one will be 1, and I will have that one, which if my p is less than 1, if my p is less than 1, let me say 1 minus 0.5, then it will give me positive. If it gives me positive, then this one will be infinity, 1 over infinity. Then this one will give me 0, 0, and this one will be infinity. Yeah, sorry. That will be infinity. But for p less than 1, then the limit n tends to infinity, integral of 1 to n is equal to limit n tends to infinity, 1 over 1 minus p to n raised to power 1 minus p minus 1. Then if my p is a value that greater than 1, yeah, this one is greater than 1, then this function will exist. Here, this one will not exist, but this function will exist. Because assuming p is 2, then you know immediately this one is greater than 1, it will give me 1 over n raised to power that number, the exact function that we are given. Then that one will be equal to, this one will be 1 over 1 minus p. So this one, 1 over infinity, to be something like 0. Then this one will give us 1. Yes. And if you see this brother, this function is converges, which is converges. If my p goes to infinity, 1 minus infinity is infinity. Yeah, 1 over this one is equal to 0, then it converges. Yes. We are going to start from there next time. And that one will give us how to look at the Hilbert ratio test, because of you because of me, read that one. Then God bless you. Till we meet next time.
Finish him. Kill the guy now. You have the gun. Hit him. What's wrong with you?
What? What is this?
Good day, sir.
You are watching Jackie Pan in my house.
No, it's King Kong, sir.
King Kong. You've never heard of ACTV before in your life? ACTV is very educative, informative, and there are football sport there. There is entertainment. There are a lot of things you can even attend lectures here. All you know is watch all those nonsense artists and do nonsense, or you watch nonsense on TV. Last night you almost came in bed with your fist.
It's not me, sir.
And you wake up every morning, the bed will be so rough, like you'll be fighting kung fu in your dream. That's the reason why you have F's in your courses, like they're specially made for you.
I have you last semester.
We £5 on you. Very stupid though. We are changing that section to ACTV right now. And oh God, the baby wants to have the first born. Stupid boy.